Alright, this is going to be about orbital box diagrams. Now this corresponds to your periodic table and your electron configurations. So if you have the S's, it has one box. If you have the P's, you have to draw 3 boxes squished together to show that they are 3 equal energy level P's. You have 5 D's and 7 F's. So please remember 1 box equals 1 orbital and 1 arrow will equal 1 electron. We'll get to those in a second. So the first rule when you're doing these orbital box diagrams is to make sure that you actually follow the periodic table. So it's called Afbau's principle. I'm sure I'm saying it wrong, I'm sorry. But it states that each electron occupies the lowest energy orbital available. So this is not difficult when you have your handy dandy cheater chart. So if you follow the cheater chart, remember we always start in the 1S's, and if we follow the numbers, we then come to 2S's, which are going to be lower energy than the 2P's, which is lower energy than the 3S's, 3P's, 4S's, 3D's, so forth and so on, following the atomic numbers. Now, you have to be extra careful when you get down here, because remember, if you are coming back up to the 70s, it would be 6S, 4F, then the 5D's. But if you're staying in the 4F's, it would be 6S, 5D1, then the 4F's. Now, you have to be very careful with this, and depending on what periodic table you're using, this one has 57 and 89 up top, but there are some periodic tables that will have 71 and 103 over here and have it completely pulled. So, again, follow the periodic table. Now, our second rule is the Pauli exclusion principle, which states a maximum of 2 electrons can be in a single orbital if they have opposite spins. Now we represent those opposite spins with either an up or a down arrow. So you cannot put 2 up arrows in the same box. You cannot put 2 down arrows in the same box. But you can, and most certainly should, put 1 up and 1 down in a box. That represents a full orbital box. Now, third rule, Hund's rule. Now it states that a single electron with the same spin must occupy each equal energy orbital before an electron of the opposite spin can be added. So if we look at our 2p example, if we have 2p1, just 1, 2p2, 1, 2, 2p3, 1, 2, 3, has to be spread out. 2p4 is where you can first get 2 in the first box, and then these would be called 2 unpaired. Oh my, we've got a mess up. So in case you didn't notice that, this should not be here. Sadly, I used pen. Should be 5, and then this is 6. Now, when you are doing, this is your example for sulfur. So since it was 1s2, off the handy dandy periodic table, we passed through the 1s2s, then the 2s's, then the 2p6, 3s2, 3p, 1, 2, 3, 4. So that looks like this on our electron configuration. Notice the boxes match. And you have the same total of arrows that you would have if you totaled up the exponents. Have a good one.